Alright, so our first example, which is also on page 249 of your textbook, if we take 1 mole of methane, we burn it at constant pressure, 890 kilojoules of heat is released, okay? It keeps the positive sign because it is exothermic, okay? Exothermic is going to have a positive, 890 kilojoules of heat is released. A lot of times we will refer to that as having, if it's exothermic, it's going to be negative, so you'll see how we would do that in the problem. Alright, if 890 kilojoules is released per mole of methane, we want to find the delta H for burning 5.8 grams. Now you may think you don't know how to do this, but it really is just using conversions. If I start with 5.8 grams, hopefully we should know that we got to go grams to moles first. Okay, so we would cross off and lose our gram units. Got a couple extra decimal places here, but doesn't change it. Then in 1 mole of methane, you release, and because it's exothermic, we give it a negative sign. Okay, you release negative 890 kilojoules per 1 mole. So all we have to do is multiply it by 890. We get negative 320 kilojoules of energy released when you burn 5.8 grams of methane. Okay. Also, one thing to pay attention to in thermo is they quickly switch between kilojoules and joules, so just make sure those units match up for those scenarios. Okay, example number 2 is also found on page 252 of your textbook. Okay, and wow, it's a bad 5, but anyway, so if I have 1 liter of 1 molar barium nitrate, 25 degrees Celsius, which really is room temperature, is mixed with 1 liter of a 1 molar sodium sulfate solution, 25 degrees Celsius, and a coffee cup calorimeter, we're going to get solid barium sulfate. Okay, so that's the chemistry. The temperature is going to increase to 28.1 degrees Celsius. Specific heat capacity of the solution, which usually when we do things in solution, we use the specific heat capacity of water, which is 4.18 joules over grams times degrees Celsius. Density is 1.0 grams. Find the enthalpy change per mole of barium sulfate formed. Okay, how do I do that? Well, first thing I got to do is have a net ionic equation, which is going to be the barium ion plus the sulfate ion, gives me barium sulfate. Then I got to figure out, is the energy released or absorbed, and what does that mean about delta H and Q, considering for signs? Well, since the temperature is going to go up, energy is released, so we're going to be exothermic, so negative delta H and negative Q. How can we calculate delta H, or heat? Well, I could use this lovely equation. And I have the delta T, I also have the SP, but I don't have the mass. But they did give me enough information to find the mass, and that's going to be using the density and the volume. Okay, so let me show you how I would set this up. Apparently there's the last answer. First, if we find the mass, okay, we take our density equation. If we rearrange it, it's mass equals density times volume. You also can use density just as a conversion factor, but we get 2.0 times 10 to the 3rd grams. The change in temperature, again, is always final minus initial, just like we're going to see a little bit later with some things. And then we plug it in. The only thing I don't like about the way that I typed this up is that I did not show you the equation first. You want to write your equation, which is going to be Q, let's see if I can get this to work, is equal to the specific heat at constant pressure times the mass times the delta T. Okay? Now, since it's a 1-to-1, we're not quite there yet, since it's a 1-to-1 ratio and the moles of reactants are the same, there's no limiting reactant. So, we made 1 mole of solid barium sulfate. So our delta H is either going to be negative 2.6 times 10 to the 4th joules per 1 mole, or negative 26 kilojoules per mole. If it happened to not be 1 mole, I simply would just divide it by the number of moles I had present to get my final answer. Okay, so sometimes those curveballs actually are not so awful and so not straightforward. Okay, example number 3 is going to be our last one. This is going to be a bomb calorimeter. So the other one, last one that we just did, was a constant pressure calorimetry situation. Now we're going to have a constant volume situation, which is a bomb calorimeter, and that's because the volume of the components is kind of locked in, right? It's just the one that's surrounded by all the material and we ignite it. Okay, so if we have the combustion of hydrogen and methane, and it's telling me that the heat capacity of the calorimeter is 11.3 kilojoules over degrees Celsius. So this is a property that's unique to that calorimeter. Okay, the combustion of 1.50 grams of methane produced we're comparing the energy released when we combust methane and when we combust hydrogen. So we took 1.50 grams of methane. We got a temperature change of plus 7.3 degrees Celsius. Okay, the combustion of hydrogen, of 1.15 grams of hydrogen, gave us a temperature change of 14.3 grams. So we need to find the energy of combustion. We're going to do per gram because that's what they gave us. Okay, per mole would just be one additional calculation. So how do we do that? Well, if I have methane, which is CH4, here's my equation. Now we're talking about constant volume calorimetry. So we're going to use delta H is equal to the heat capacity of the calorimeter times delta T. So we've got that 11.3 kilojoules over degrees Celsius times 7.3 gives us 83 kilojoules for this particular reaction. Since we combusted 1.5 grams, we got to divide it, and that's going to tell us that for methane, we release 55 kilojoules of energy per 1 gram of methane combusted. Hydrogen, we're going to do a very similar process. We're going to set up the same equation with the heat capacity of calorimeter times the delta T. So this time it's 11.3 times the 14.3 temperature change. And again, we have to divide it by the amount of grams that we had. So for hydrogen, you get to release 141 kilojoules per gram of delta H, okay, or of energy. So if we're comparing them, the energy released by hydrogen is about 2.5 times the energy released by the methane when it's combusted. And these types of calculations are things we do all the time when comparing different energy sources and selecting different things. So I hope that helps. If you still need some help, read your textbook or go to the Khan Academy videos or ask me some questions during class.